Hey folks, this is Mr. Tam here, trying to keep you guys in the loop despite missing all this school. We're going to try to keep up the pace to finish the course. Now, when we last met, we were talking about the amount of energy either absorbed or released by a system. And today I'd like to, one, show you the factors that influence how much energy something could have, either releasing it or absorbing it. And I'd also like to kind of help you visualize this using a graph of some sort. So first things first, I want to present to you this particular reaction right here. As you could see, you're taking C8H18, which we can also call octane, which is a type of fuel, which is actually something we find very commonly in cars. It's gasoline. We're going to combust it with some oxygen, and we get our usual suspect products in the form of carbon dioxide and water. So, needless to say, in a car, you can't just leave the gasoline in the tank of gas and have it react. You need some kind of energy to actually start the process. So, to this reactant side, what I'm going to do is I'm going to add in a certain amount of energy. Now, we're just going to leave it as energy for the time being, but I'm going to specify it in saying that we have this energy found in the spark plug. And also on the other side, as you can imagine, engines of cars get extremely hot. And this release of heat is actually also energy, but at a greater magnitude. I'm going to write here hot engine, and basically the ability to move a car. Now, that being said, we can essentially assign some kind of comparative value from the energy on the left to the amount of energy on the right. So the amount of energy on the left, let's say that you're looking at 1,000 joules. Pretty typical of a spark plug, but if you compare that to the amount of energy that is released on the other side, well, you're looking at somewhere in the probably million range of joules. For example, now, if you compare the two amounts, you could clearly see that the amount of energy released by this combustion reaction is way higher in comparison to the amount of energy originally used to actually get this reaction started. So where is the energy larger? Is it on the product side or on the reactant side? Well, in this particular case, you have a greater amount on the product side. So if there's a greater energy on this side, and on this side, of course, it is in excess of essentially 999,000 joules in excess, then we know that our change in delta H is greater on the product side than it is on the reactant side. So this is what's going to give us an exothermic reaction. Now, that was just kind of like to give you an idea that even though there are two energies that could potentially come into play, you always look at a comparison between the two sides. So what could actually influence the amount of energy that each of these substances can have? Well, let's write out here what can influence the amount of potential energy. Well, we're going to start off with just listing a couple of factors, one of which could be the type of chemical bond. One could be the number of chemical bonds. Followed by the temperature. And last but not least, the state of matter of the specific substance in question. So we're going to take a moment. We're actually going to look at all four of these factors and see how we can actually influence the enthalpy of each one. So first, we're going to look at the type of chemical bond. This is a bit of a throwback to secondary 4, where you're looking at ionic versus covalent. Now remember, covalent is essentially a sharing of electrons when two nonmetals do not want to part with any of their electrons. Whereas when you look at an ionic bond, you're looking at one substance or one, we'll say element in this case, wanting to give up and the other one wanting to take it in. And the fact that they now have opposite charges is what leads them to attract one another. You're going to notice a lot that in nature, often things that are extremely stable, such as the nitrogen that we find in our air, such as the oxygen that we breathe in, are all covalent bonds. So sharing electrons creates a much stronger attraction between the two elements in comparison to, let's say, something like salt, where if you essentially put salt into water, the waters can essentially get in the way of the salt and break the two molecules up, thereby leading them to separate again into their ionic form. Whereas something like nitrogen is extremely difficult to separate. So in that regard, if you need more energy to cause them to react, well, this one will have a greater enthalpy. And this one will have a smaller enthalpy. Enthalpy, of course, is just a very fancy way of saying what is the amount of potential energy each of these substances has. So the next factor we're going to look at is the number of chemical bonds. So let's say I were to take, for example, methane, which is a very common greenhouse gas, CH4, and draw it out using Lewis dot. Okay, we're going to use this Lewis dot structure right here just to simply sketch it. And we're now going to compare this to, let's say, I don't know, let's draw in propane, for example. And as you could see already, the fact that I have 3 carbons leads me to have to draw more bonds between the molecules or between these atoms. So just by visually seeing this, we can pretty much say that you have 1, 2, 3, 4 bonds that are between carbon and hydrogen. And then here I can count it out: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds in comparison. So to break apart all these bonds, well, there's just way more to break when it comes to propane, which is this one right here. Therefore, this one contains the greater amount of enthalpy, or the greater amount of potential energy that it could release. Okay, so this one has a higher enthalpy, and this one has a smaller enthalpy. And that's pretty much what factor number 2 is, just comparing the number of bonds. The more number of bonds something has, the more likely it is, or not more likely, but basically you're looking at a higher amount of potential energy it could release. So that does it for 2 of the 4 factors. We're going to now move on to the third one. And the third one is the temperature. Now the temperature is pretty straightforward to explain. If I were to just draw you 2 beautiful ice cubes right here, one found at -10 degrees Celsius, and and another ice cube found exactly the same size at -30 degrees Celsius. you have to actually take more heat out of the -10-degree one to get to the -30-degree one, which means that the fact that -10 degrees Celsius has more energy means that it has a greater amount of enthalpy. So the higher the temperature, the greater the amount of enthalpy. So temperature is a pretty straightforward factor that we can consider. And last but not least, we're going to look at the states of matter. When it comes to comparing solid, liquid, or gas. Now, when it comes to these three states of matter, we have to remember that each one has a variety of movement, one more than another. So gas, as we know, has 3 types of motion. And we can list them off as translational mainly. And then you have a bit of rotational and vibrational. And as you get colder and colder, you start losing those degrees of freedom, if you want to call them that. They get tighter and tighter and more bound together, so they move a lot less, leading to eventually us getting to a solid point where you have essentially just vibrational motion left. So the enthalpy is greatest here in comparison to the enthalpy found at liquid, and then the enthalpy found at solid is indeed the smallest amount, simply because there's less movement when it comes to the solid state of matter. Now, this is presuming that, of course, we're comparing the same substance. Let's say, for example, you're looking at an ice cube, you're looking at some room temperature water, and then you're looking at some water that's been just evaporated in a pot, for example. So the water that's found in the pot will obviously have the greatest amount of enthalpy, meaning it has the greatest amount of energy that it could release, followed by liquid, and then solid being the one that has the least amount. So that being said, we've now explored all 4 varieties or all 4 factors that can influence enthalpy. And those factors, just to recap, are the types of chemical bonds, covalent versus ionic, the number of chemical bonds, the temperature of the specific substance in question, and of course, to tie that in, the specific state of that substance. Now, we're going to move on now to the second portion of this class, in that we want to be able to visualize what enthalpy looks like when we plot it in a graph. So let's start off by drawing our 2 axes, as we are used to doing. So I'm going to draw a nice big graph here and try to help you guys visualize this as much as possible. What I'm going to draw here for you is obviously a little bit simplistic, and there are going to be numbers that I will be making up as we go along, because I don't really have any numbers on hand, but the concept could be explained using these numbers that I'm going to make up for you guys. So what we typically see with enthalpy graphs is something that looks like this. We have, basically on one end, let me just finish up here. Alrighty. On one axis, we have the reaction progress. And on the other end, we have the amount of potential energy or enthalpy let me write in potential energy. So it means that there's a certain amount of energy that those particular bonds, if being tampered with, could release. So let's use a very simple reaction that you guys have seen time and time again. We're going to react methane to 2 oxygen atoms, or molecules in this case. And what you're going to end up with at the end are your products on this side being carbon dioxide and water. And then there's this weird intermediate, this weird plateau that for some reason should be where that arrow is. And yes, that arrow that you've been learning to write this whole time has actually some aspect of importance to it when it comes to enthalpy. So when you react this methane molecule right here with the 2 molecules of oxygen, first we have to give it enough energy. So I'm going to label each of these sections with a number. And we're going to label these numbers together with a definition that will help you explain all of this. I have number 3 all the way up here. Number 4 that actually shows you it's going down. Number 5 all the way here. And of course, the one that people tend to forget, this one right here, number 6, is the gap between your reactant versus your product. So, first things first, number 1. Well, number 1 represents the potential energy of reactants. So let's make up some number here. Let's say we get to, I don't know, 3,000 kilojoules, just for argument's sake. And you'll notice that at number 2, there's a big jump from 3,000 to, let's say, we get all the way up here to 6,000, just to make our lives, let's go 5,000. Doesn't have to be to scale. 5,000 kilojoules. Now, that number 2 actually represents the amount of energy you need to input into the system to get those bonds to break apart. Now, remember, these methane molecules are attached, or that carbon in the methane molecule is attached to 4 different hydrogens. And in order to be able to get access to that energy that's found in between those bonds, you need to break it apart first. And number 2, we call it the activation energy. And the way I like to describe it to students is to say, you know what, there's a hill in front of you, there's a soccer ball. It's essentially the amount of energy you need to put into the ball to get the ball to go over the hill. If you don't put enough energy into it, then the reaction will not occur. So that activation energy is essentially what you have at the top, which is your 5,000 minus your 3,000 energy, kilojoules of energy they started with, and you end up with a difference of 2,000 kilojoules. So this particular activation energy for this reaction is 2,000 kilojoules. So that's a good start. Our reaction is now proceeding, and as soon as they get enough energy to react, you're going to notice that they separate into their elemental states, we'll call them. And all these, of course, are atoms. And as you guys may or may not remember, oxygen, for example, is not very stable when found alone in nature like this. It really wants to be bound to a second oxygen atom. So this state right here, number 3, we call it the activated complex, is a very quick state in that This happens for but a brief millisecond. So for a brief millisecond, all of the reactants are now separate. They're not bound to each other. They're in their free-floating atomic forms, and they float around there, very unstable, and are ready to form new products. So the activated complex is that 5,000 kilojoules of energy. It's achieved a very high state of energy. But what goes up must come down. So number 4 is that drop in energy. When they form their new products, we call this the energy of formation. Also, we can call this the energy released. Because when those carbon atoms combine together with the oxygen, and those hydrogens also combine with the oxygen, they come together, and when they form bonds, they release energy. And that, let's say we get to number 5. We now are at, let's say, for argument's sake, 1,000 kilojoules. So there's a big drop. As you could see, it essentially goes from 5,000 kilojoules to 1,000 kilojoules. Now, because there's a drop, okay, that energy is being released by the system, you essentially end up with 1,000 kilojoules, which is what it ends up at, and you started at 5,000 kilojoules. So overall, you actually end up with 4,000 kilojoules. So this is the amount of energy released by the system. All right, now we're at the final part where you're looking at the potential energy of the products. And that, simply put, is where it ends up being only 1,000 kilojoules, like where its level is at. But that is not the most important of all the numbers. The most important of all the numbers I've left for last. In fact, it is number 6. Now, number 6 is what we call the delta H, the change in H. This is the one that we've been studying this whole time when we're talking about Hess's law, when we're talking about dissociation, when we're talking about releasing and absorbing energy. This is the sum of the potential energy of the products and, let me just rephrase that. We're going to say that it's the energy of, we'll say it's the potential energy of the products subtracting the potential energy of the reactants. So in this particular scenario, you have 1,000 kilojoules, and you're going to take away the 3,000 kilojoules that it started at, and you'll notice that it's a net difference of negative 2,000 kilojoules. Now, we've seen this before. When you have a negative energy, that essentially means that overall, your system released more energy than it did absorb. You can clearly see that when you're looking at the amount that you needed to put in versus the amount that was released. So let's say that the energy released was negative 4,000. So when you add these two numbers together, you can see that there's a greater drop in energy compared to the amount that was given in at the beginning. So we can conclude that this particular reaction is an exothermic reaction. Now, you can probably gather already that, I want to draw a little graph down here. If I started off with a specific energy here, I went up, I have my activated complex, and then the drop in energy, let's say, was not as extensive as are exothermic, but our potential energy for the products ends up being higher than that of the reactants. Well, in this particular scenario, we have what we call an endothermic reaction. Now, this should start you guys off well into chapter 4. So what I'm going to do is I'm going to leave this up on my website so you can download it for those of you who didn't bring your stuff home. But you can essentially start reading it and hopefully making some sense of this. I'm hoping this helped a little bit. I'm wishing you guys very well, and I will see you in the next lesson. Bye.